Welcome to Part 4, the final section of the tutorial on the SAS system for Windows. In this video, we will cover some basic procedures and how to capture results of a data analysis. I'll introduce you to a couple of the base procedures that are helpful for managing and checking an analysis. The first procedure is the print procedure. This is a technique to cross-check the data before analysis. Through this procedure, you can obtain a listing of the electronic data set to confirm it has been interpreted correctly and that the calculation of new variables are correct. To list the data set, use the procprint command. I'll include a run statement. What this command will do is provide a listing of the most recently created data set. Another useful procedure is the sort procedure. Through this procedure, we can sort the data set using one or more variables. This is helpful when calculations are being performed or when extreme values are being searched for. If you sort the data file by the variable under question, the missing and smallest values will appear at the top of the list and the largest will appear at the bottom. That is quite helpful when the data set may run hundreds or thousands of lines. I'll include the sort procedure before the print procedure. In this example, I have invoked a sort and I am sorting the data set by the variable WT100. I have included a run statement to ensure that the sort is finished before the print. Notice that I can place these statements all in one line, so long as I am separating them with semicolons. Normally we would list them line by line because it is a lot easier to edit when checking for errors if you place the statements on individual lines. By default, SAS will use the last data set created when a procedure is specified. Sometimes you may want to have it do the procedure with another data set other than the last one created. This is when the naming of data sets comes into play. In each procedure statement in the SAS system, you can point to a specific data set for the program to perform the analysis with. To do this, you include a data equal option in the procedure line. I did not have to do it for this example, but I will illustrate how this specification works. In the sort procedure, I will include the data equals second in the command line. And I will do the same in the print procedure. Now both the sort and the print procedures will be performed with the second dataset. To complete a sequence of tasks in the editor window, make sure the last line has a run statement with a semicolon. To submit the series of statements into the SAS program, you can either use in the top ribbon the Run Submit option, or along the second line you can click on the symbol with the person running. SAS has now performed the series of steps and has presented the results in the results window. However, do not look at the results until you have first checked the log window. You need to confirm that there are no problems in the analysis. This is one limitation with the SAS program. It automatically takes you to the results. Do not look at those until you have first checked the log window. So I will now switch to the log window and scroll to the top. The log reports what SAS did with each statement. You will see it identified an error in the first line and made a correction. It assumed the error was a misspelling and gave a green warning. If this change was fine, then you can proceed. Sometimes the self-correction is not what you want. The next section below is the creation of the first dataset. It found 20 observations and 4 variables were created. That should correspond to the expected number of observations in the experiment. In this study, there were 10 replicates of 2 species, for a total of 20, so that is correct. The rest of the statements do not appear to have any errors. If you find red lines in the log window, this indicates problems that SAS could not self-correct. You need to correct these errors before proceeding with interpretation of the analysis. Since this log is acceptable, we can go back to the results window. Here is the data listing with all 20 observations sorted by the 100 seed weight. We can also see that the values conform to our original data and the calculation of the new variables appear correctly. The log and results windows are cumulative windows. New results will be appended to whatever is already there. If there are problems with an analysis, use the log window to identify where you need to make the correction to your command. For example, I will go back to the editor window and I'll make my correction and resubmit my statements. The error I had was in the first line, and I had misspelled the command title. I have missed the E to it. Now that I've made that correction, I will now resubmit the statements. The results for this second submission have been appended to the results from the first submission. Normally, you would not want to do that, especially if there are errors in the first submission. You don't want to have the results file containing erroneous information. So to clear the results view, select the window, and using the ribbon options, select Clear All. And what that does, it clears the window that was active. Also, go to the log window and do the same. And now we can return back to the editor window. By doing these steps, we've now cleared the results window and also cleared the log window. So now if we resubmit statements, we will only have the results of a correct analysis, and we'll only be dealing with the log report of that last analysis that we have conducted. There are also two other base procedures that can help you with data analysis. The first is the SG scatter procedure. It does not generate publication-ready graphs, but it can be a quick way to visualize the distribution patterns in the data. This is helpful in confirming trends, or more critically, absence of trends and error distributions in an analysis. To generate a scatter plot, use the proc SG scatter command. The SG scatter procedure lets you do a scatter plot of any variable against any other variable. So one of the variables we have an interest in this data set is the 100 seed weight. So the WT100 variable is an obvious variable to consider. We do have two classification variables, one being the species, the other is the replicate value. And so those are also variables that we could perhaps look at the distribution patterns in terms of the 100 seed weight. So what I will do is generate a scatter plot involving the 100 seed weights against those two variables. With the plot statement in this procedure, the variable on the left of the asterisk is the variable that is placed on the y-axis or the vertical axis of the graph. And on the right-hand side, you would list one or more variables in which plots would be created. And placing them in brackets, we can then have multiple requests of plots. And so with this statement, the 100 seed weights will be plotted against each replicate, as well as another plot of 100 seed weights by species. I'll now submit these commands. So now we have two scatter plots created. One on the left is the 100 seed weight against replicate, and the one on the right is the 100 seed weights against species. Through these plots, we can start seeing some of the trends in the data. For example, the sunflower values in terms of 100 seed weights are much less than the corn values. But in a variance analysis, we're much more interested in looking at the residuals and making sure that we have random distributions of residuals as well as normal distribution. So instead of plotting the observed values, which are the 100 seed weights, we're much more interested in plotting the residuals out of the analysis. So I will now switch back to the analysis and add the statements to do a variance analysis of this study. In this particular experiment, it is a completely random design with species as a classification variable. So I will now do a Glimix analysis and divide the variation into that classification group. The statements I've added will give us a variance analysis of the 100 seed weights using the proc-Glimix program. Species was the classification variable. I've requested the means for the species, as well as I've generated an output data set I've called that data set third, and this will have the individual experimental unit values, as well as columns for the predicted values, the residuals, and I've also requested the studentized residuals. And these variables will be called predicted, residual, and SRESID in the dataset. I've now done a change to the SG-scatter request, and I'm now having it plot the studentized residuals against replication and species. I'll now submit these statements. So now we have scatter plots of the studentized residuals for each of the replicates, as well as each of the two species. With the studentized residuals, we can now start seeing trends and patterns, and there is one particular value in the sunflower that seems to be very far apart in terms of its distribution pattern relative to the rest of the observations. This particular value is a putative outlier, and through analyses of the data set itself, it was an error in recording. So these plots let us look at the random type patterns of the residuals. If you look at the sunflower and corn distributions, the corn distribution is fairly wide, generally a reasonable spread. So with a variance analysis, one of the core assumptions that need to be met is random distribution of residuals or random distribution of errors. The other type of distribution pattern we also want to see is a normal distribution of the errors or the residuals. So I'll now switch back to the statements. So for this example, I will add another procedure called proc univariate. And through this procedure, I'll be able to generate a graph of the distribution with the expected normal distribution superimposed, as well as perform a statistics test of normality. So I'll first invoke the proc univariate procedure. So these set of statements, and I've indicated a normal option as part of the procedure call, and what that does is it generates statistics tests of normality. I've also indicated what variable to do the test on, and that is the variable studentized residual. With this procedure, the histogram statement generates a frequency distribution of the variable indicated, which is the studentized residual, SRESID. The options to the statement, normal and kernel, superimpose on the frequency distribution the normal probability curve, as well as a curve that is based on the data distribution itself. We can generate one of these graphs for all the data placed into a pile, or we can subdivide it for a particular classification. We can add another statement, the by species, to this procedure. So long as your data set is sorted by species, you can add by species, or whatever variable or variables that you are interested in looking at graphs in terms of subdivision of your data set. So by placing all of these statements together, we can now generate a visual diagram of the distribution, as well as perform a statistical test of normality for each one of the species in terms of the studentized residuals in the analysis. But in this particular example, we're using the third data set for generating our graphs. The third data set has not been sorted by species. Only the second data set has. So we'll have to add in, prior to this procedure, a sort to ensure that it's sorted by species. I'll now submit these statements. I'll scroll back through the results to get the distribution graph for corn. The frequency diagram is illustrated with the bars. The blue line is the expected distribution based on normal probability. And the red line is the kernel, which is the distribution based on the data itself. As you can see, those two lines reasonably follow each other. Yes, there are a few little squiggles here and there, but visually the observed and predicted are not deviating very markedly from each other. But a better way of assessing does that distribution differ from a normal distribution is to apply a statistics test. So I will scroll back just a little bit further in the results to the summary of the statistics tests of normality. In this procedure, there are 4 tests that are automatically generated. The Shapiro-Wilk test is the first one listed, and that is one generally applicable to a lot of situations when you're dealing with a Gaussian type variable. In this particular test, this W statistic is 0.93. More importantly, we look at the p-value. The p-value is 0.45. So at a typical type 1 error rate that we would assess at 5%, that p-value is well above that, and we would accept the null hypothesis that the distribution follows a normal distribution. So as we go back and look at this distribution again, what we are seeing visually corresponds to the statistics test, indicating that the distribution pattern does follow a normal distribution. Now let's consider the sunflower. Sunflower has a very different distribution. You will see that there's 2 peaks visually. The red lines are the distribution pattern using the kernel option. The blue line is what the distribution would be expected to be if it was a normal distribution based on these variances that are inherent in that data set. So obviously visually there seems to be 2 peaks, and that would not be a normal distribution. So as we go back and consider the test of normality, again looking at the Shapiro-Wilk test, the statistic is 0.54. The p-value to that statistic is less than 0.0001. And so we would reject the null hypothesis and declare that this distribution deviates from normality. And so once again, the statistics test and our visual assessment of the distribution correspond. And so something about this data set is not, the sunflower values are not following a normal distribution. And the reason for this in this particular example is because of that one observation, and that observation was an outlier because there was an error in recording the value. If that data point is taken out, then the distributions actually do follow a normal distribution. I'll now illustrate how to capture information for use in other programs. Images in the results area can be captured by hovering the mouse over the image and doing a right click, and you can save the picture. And you can save the picture as a PNG or as a bitmap file, and then use that in other programs. If you're dealing with tables, so I'll just go up to the test for normality. If you hover over the table, again do a right click, you can export the table to a Microsoft Excel program. And that way you can very quickly capture a particular table out of the results area. If you hover outside the results area and export to Microsoft Excel, here you will get all possible tables that can be generated in terms of an Excel spreadsheet. And this program will then let you go through that entire result area and indicate which particular tables you want to export. And so you can do a whole series at once. You can also save the results table using the File Save As option, and you can export it as a web archive or as a HTML format. You could also print, and you could print it as a PDF document. So those are some different ways of taking the results and saving them in different formats that you can then import into other applications. SAS also has an export method for the electronic data sets themselves. To export these, go to the ribbon and select File, Export Data. Select the data set you want to export. In this case, we have 3 electronic data sets. One I've called first, one I've called second, and one I've called third. Let's go to and use the third data set. And that was the one that also has the residuals and predicted values. Click on Next. And this lets you then define what type of format and what type of program you are going to move this electronic data set into. The SAS system that's installed is a 64-bit application. And so if you have a Microsoft Office system that's also 64-bit on your computer, you can export it to the Microsoft Excel workbook. However, if your Microsoft system is a 32-bit, you cannot use that option. You have to change the particular export system. And if you have a 32-bit, one of the ones that works fairly efficiently is the one option called Microsoft Excel 5 or 95 Workbook. That seems to work with a whole series of the 32-bit systems. Click on Next. And then you get to choose where you're going to save the file and indicate what file name you want to use. So I'll use the Browse button to indicate, in my case, I'm going to send it to the desktop, and I'm going to call this one Example. And I'll click on Finish, and that file has been generated. I'll now go to my desktop and open up that file. So this is the Excel file of the third data set. You will see that it has the rep and species and WT100 variables that were in the original data set we submitted to the SAS program. It's got the 2 additional variables that were calculated, the weight in milligrams, the natural log of the 100 seed weight, as well as we've added the predicted values, the residuals from the variance analysis, as well as the studentized residuals. And so you can use these in other applications. I'll now switch back to the SAS editor window. So now we have a set of statements that includes all of the data, all of the calculations, all of the variance analysis, and all the procedures that we applied. We can save these SAS statements. And so we can do File, do a Save As, give it a different name. And that way we can recall those statements at a future time for further analysis of this study, for changing particular applications that we may be doing with the data. Perhaps there's another run of this study we can now add in and do a further analysis. Or we can also recall all of these statements again for some other application. An advantage of saving the statements along with the data. So here are the statements, and we've got the data along with it. It helps you in future scenarios because you don't have to go hunting for the associated data files. The data and the text are all together, and these are just simple text files, and they don't take up very much room. A couple of other additional points about the SAS system. When you report on an analysis, you always need to convey what program and what version was used. To determine which version you are using, select Help and About SAS from the ribbon. The window indicates that this is SAS version 9.4, and that is what you would include in the methods section of a paper or a thesis. Also, the package includes a help reference to all procedures, statements, and options available. Again, to access these, under Help, go to SAS Help and Documentation. Open up SAS Products, and SAS Procedures options gives you a summary of all procedures sorted by name. You can now go to the particular procedure you would like help with. So I will open up the Glimmix procedure. The help files for procedures are all organized the same way. The system provides an overview, a getting started, the syntax, details, example datasets, as well as all references related to the procedure. Syntax gives you a link to all possible statements and all possible options that are available that you can use. Some of you may be doing a repeated measures analysis, and you would have to indicate what repeated measure covariance structure you would want to specify. In Glimmix, that is specified using the random statement. So by following the hyperlink for the random statement, you can then access what are the whole series of options that are available to that statement. And so table, in this particular procedure, table 44.17, gives the entire list of options that are available for that particular statement. This involves the covariance structure itself, how smoothing is applied, and what statistical output you are requesting from that procedure. The actual covariance structure would be specified using the type equal option. Following that hyperlink, you can then obtain the entire list of all particular covariance structures. You will find hyperlinks to the original papers or published text, which explains the application and the limitation of various options. And so you can use those to identify which is the most appropriate option for the type of data or situation that you're accounting in your analysis. This concludes the tutorial on getting started with the SAS system. For those of you who are using the University Edition, there is one additional introduction tutorial which covers some of the unique features of that particular package.